we now move to the plenary PODS keynote given by Jan van den Bussche. The keynote was selected by the PODS Executive Committee. So Jan, I know Jan very well, but I'm going to read off my phone anyways. But Jan is a professor at the Data Science Institute at Hasselt University in Belgium. He has been active in database theory research since 1989, and he received his PhD from the University of Antwerp in 1993. Jan, he helped to establish what one might call, especially if you're a Belgian school in database theory, of which there are many respected members of the PODS community part of it, like, for example, Jan Paradans, who is now retired, Stijn van Summeren, Frank Neven, Wim Mertens, Bas Ketsman, Mark Gijsens, also retired now, and myself. These are just a couple of examples that are kind of coming from the Belgian School of Database Theory, which Jan helped to start. Okay? Jan served as program chairs of ICT of PODS. He also chaired the ICT Council. He was also the PODS Executive Committee chair, the general chair, and he's also like an ACM distinguished member. Broadly speaking, his research interests revolve around the design and analysis of data models and query languages for a wide variety of data and computation settings. Okay? So on a personal note, Jan was my PhD advisor no more than 25 years ago. I know it's unbelievable if you look at me, but that's true. And I learned from him at least 4 important things during my PhD. And so here we go. First, how to abstract a problem until you reach its core, and then you can finally start solving it and come to the essence of the problem. That's number 1. Second, if you can write things down clearly, please do so, even if it makes things look simple. It's a very important lesson. Number 3, where to stand at the conference to maximize the chance of getting food at the reception. This is really something that, and of course his height helped a lot because he could look where the waiters are to bring the food, right? Very important. And then finally, perhaps most importantly, to pursue research directions that generally interest yourself and that open potentially like new questions in the field, right? So really kind of coming from your own interests and desire to do good research. And so today's keynote is a perfect example of that spirit. Jan will explore how machine-learned models can be managed, how they can be queried like data, using expressive database query languages or database languages, and at the same time he will highlight emerging research challenges. So please join me in welcoming Jan van den Bussche to the stage. One moment. Anon DC, enjoy. Okay, that should be the word for enjoy. Yeah?
Okay, can you hear me? Yes? Okay. Thank you, Floris, for the kind introduction. And so, yes, I would like to talk today about my idea that models are data too. It's not my idea, I will make that clear. Many people have the same idea. And so I want to investigate together with you the notion of expressive querying of machine learning models. So, of course, we are currently in the machine learning era and we are facing a deluge of models. I don't have to tell you that machine learning is ubiquitous in science, engineering, society in general. Worldwide, worldwide, millions of models are being generated. That's worldwide. That is just people sharing their models around the world on global repositories. And actually also inside the enterprise or within data science research projects, also a large numbers of models are trained, tested, deployed, archived, etc. Now, before we really get started, I would feel most comfortable if, when I say model, you don't immediately think of large language models or like the models of generative AI that we have now, but maybe think more of models that are trained for dedicated, well-delineated tasks. Because nowadays, of course, these dedicated tasks, we are now in the zero-shot learning era. And so we use also these large foundation models also for well-delineated, dedicated tasks, but you should not forget that in practice, these let's say, models trained in the classical way for dedicated tasks are still very important and still used a lot. I mean, these are why? Because they are small, they're efficient, they're reliable, and so people want to rely on them and they are used. And that is probably the kind of models I will be talking about today. Okay? Just to make sure that we're on the same page. Now, since these models really encapsulate important knowledge, and since these models are everywhere and they are very valuable to us, we should manage them and treat them like all other valuable data. Yeah? So we should manage them in data systems. Yeah? And okay, you will probably agree with me that one of the main reasons why we use a data system in the first place is because it has these powerful query facilities. Yeah? So allowing querying is a core purpose of a database system. So the logical conclusion is, if we want to see models as data, we should also be able to query our models, because we are used to querying our data. And so together with you, I want to go through the question of what that even means, because when I talk to people about querying models, they ask me, yeah, what do you even mean by that? Yeah? And so we will go through that together. Yeah? So the outline of my talk is the following. First, I will take a step back and give you a little bit of history, early history on querying models. Then I will present a kind of a taxonomy of querying models, different aspects of querying models. Yeah? Some kind of small taxonomy that I propose. That's the second part of the talk. In the third part of the talk, I will zoom in on some of my own work in this area, recent work that we did. And finally, I will conclude. Okay, so let's first step back a little bit. And the first thing I would like to do, it is a bit of a pet peeve of mine maybe, is that the word model is probably one of the most overloaded terms in science. I mean, and let's cycle through a number of meanings of that word that are used. So, for example, yeah, in statistics, people use the word model to describe mathematically a population. Yeah? Population of data with a certain class, parameterized class of probability distributions over that population. That is a word that is used. We will probably not use it in that term. Of course, also, for example, in computer graphics, people talk about 3D models, which is something totally different. Yeah? It's basically a data structure. Yeah? Now, closer to home, closer to database systems, like more than 20 years ago, Phil Bernstein launched this entire research area of model management, but there a model meant really essentially a database schema. And there people were concerned about mapping between schemas, composing such mappings, inverting such mappings, etc. That's also not really what we are going to do, also called model management. Then another meaning that you often hear in science in general, a model for a problem is basically a solution to the problem, often implemented as a program, as code. So model is also often used in the meaning of code, program code. Of course, like I said in the first slide, we will think of a model as a representation of a function that is learned using machine learning methods. So that is the meaning we will be using. But there are more. I mean, for example, in mathematical logic, yeah, because that is an area that is close to my heart, dear to my heart in mathematical logic, the word model is used also just as a word for a relational structure, so basically a database instance, possibly infinite. Yeah? Also the word model is used there. And that's interesting because I want to view models as data, so I want to view models as models, if you want. Yeah? It's a bit of a pun. Yeah? And finally, also in databases, we use also the word model in the sense of a data model. Yeah? And a data model, what is that? That is the design of a schema language and a query language so that we can organize our data logically. That's also the word model. And you see, some of these meanings will be irrelevant for us, but at least 4 or 5 of these meanings will actually all be relevant here. If you want, what really want to ask is, So can we somehow develop a logical data model for models? Yeah? Good. Now, I said that I was going to present a little bit of history. Yeah? And so I want to do that according to the fourth meaning here. Let me use my pointer here, maybe because I will need it later. The fourth meaning here, so the meaning of a model as program code. Because indeed, I mean, already more than 20 years ago, Jim Gray emphasized this. Yeah? And I can quote from, for example, the Lowell Database Research Self-Assessment, which was published in 2005, so more than 20 years ago, where there is literally, this is a literal quote from that report that I know because Jim Gray at the time during panels emphasized this point repeatedly. People who were there will hopefully remember this, that we would like to see code become a first-class citizens of a DBMS. That is mentioned there. Now, if we are honest, this didn't really happen, right? I mean, we are not, I mean, our code repositories are not in our data systems, so that didn't really happen. But I still think it is intriguing and interesting. But at the same time, if we go even 20 years earlier back to Mike Stonebreaker, yeah? Like one of the first developers of an actual database system. So in the very first designs of the first relational database systems, there was already code in the DBMS. So there is this very old paper from 1984 called Quell as a Data Type. You're not supposed to read the paper, I'm just showing it here for illustration. But there, that was in the system, so this was in the design of early Postgres, basically, where Quell was the query language. And already in that early design, Quell was a data type. So you could store in your employee table, for example. You can see here the, where is my cursor? Yeah, you see here the hobbies column of a tuple, and the content of that tuple is code. Well, what is the most important code in the database systems? That's our query expression. That's also code, right? So there is code there in the table. And in queries then, you could actually just run that code automatically. When you retrieve the code, when you retrieve the column, it will execute the query. So this is something that is already 40 years old, and that was already there, just as a historical backdrop. Now, I also was young at some point. Yeah? And so here you see a photo of me like maybe more than 35 years ago. And I was really inspired by that. Together with my co-advisor, Dirk van Gucht, I was really inspired by this idea of querying code and managing queries, basically, query code, query expressions inside a database. And so one of my first PODS papers after my PhD, I had a number of PODS papers for my PhD, but then things that I did as a young postdoc. I think it was the first after PhD PODS paper I had here. That was really about this. So where we try to formalize this idea of, okay, you have relational algebra expressions in a database, and how can you then manipulate these using the relational algebra? We call that reflective relational algebra. And we had some follow-up work also with three of my first students actually, or two, Frank Neven, who is here, and Stijn van Summeren, also together with Gottfried Vossen, who was also one of my mentors at the time. And so this really explains why I'm still excited about this now. Yeah? What is now the new code? The new code now are models. And so I'm still interested in this querying of code of models. That's basically why I'm standing here, trying to revive this interest. Yeah? Good. So, like I said, let's get to work now. Let's start with presenting some kind of taxonomy. Don't take it too seriously, but I think it helps to understand what we mean by querying models. And so I have four categories. I have administrative querying, that I call it. I have applicative querying. I have behavioral querying. And finally, I have looking inside models. So these are the four categories of model querying that I would like to go through with you today. So let's start with administrative querying. That is basically something that we already know very well how to do. Yeah. People in large data science projects commonly use popular ML platforms. For example, ML Flow is a very popular system. And those systems, they help you to keep track of your models. They keep track of the training data, they keep track of the models, they keep track of when you deployed them, when you trained them. They will keep dates, they will keep lots of other metadata related to this. So that is what I call administration. I mean, you have to keep track of where is all my stuff, and for that you have already good platforms available. Then on, let's say, on the world scale, because this is on the, let's say, on the enterprise scale. On the world scale, there is also something like that, which are the so-called model zoos, where people share models all over the world. For example, Hugging Face is, of course, the most important, the most well-known of these model zoos. Public repositories with millions of models. Sometimes people also call them model lakes. It's a bit maybe a more respectable term than model zoos. And these platforms and also these model zoos, they support some kind of querying. But querying there really has to be interpreted as searching based on, filtering based on attributes. Which model did I deploy? Which model did I deploy on this, or which model did I train on this data 1 month ago? Or which model was developed by Floris? Lots of metadata that can be attached, and you can then retrieve it. So this is simple search and filtering, the thing that you expect. And that's what I call administrative model querying. This is not a problem. This is, well, we know very well how to do that. Now, interestingly, model zoos are also taken up in the machine learning community. And they have their own spin on it. It is very interesting. They also have, I mean, our motto is models are data too. And they also know that. I mean, and they are taking that seriously, but they are using that, they are approaching this from their own perspective. And I want just one small side note on that. I have one slide on that because I think it's interesting, and probably, I mean, we have to connect more with the machine learning community on this kind of things, because they approach it as follows. So they have things called model atlases. Yeah? So this is a picture that I took from Elia Horowitz's website, and he tries to visualize huge graphs of models. So every point that you see is a model. An entire model, even big one, because these are actually large language models, but people also use this, for example, for vision models or image recognition models. For all kinds of models, this is being done. So every point is a model. And then you see that there are some edges between models. This is based then, for example, on certain distances between the weights of the model. So every model is viewed basically as one huge weight vector. Yeah, a long weight vector, and this is managed. And so the ML people, they are typically interested then in mining for structural patterns, predict properties of models based on the weights. Can we predict that the model will not over specialize, for example? Can we somehow predict that based on patterns? Or they even train models on this data. So that's really mind-boggling. So they train models on this data, but the data points are models. Yeah? And so that they even have generative models. So just from given, that is like zero-shot learning on steroids, basically. You just give a few examples, and it will simply generate a model, but not from a foundation model, but simply trained from all these models. So this is the way how ML people look at it, and I just wanted to inform you about it, because when I learned about this, I found it quite exciting. Okay. But okay, let's get back to our main trajectory. We were talking about this taxonomy. So I talked about the administrative querying. Now let's go to applicative querying. And applicative querying, that is really quell as a data type, basically. But now in the applied, not to query expressions, but to models. The idea basically is that you can call models inside queries. Yeah? And this is now also something that is receiving a lot of attention, yeah? And I call that applicative model querying. By the way, managing models in databases, including calling them, but also training them and integrating these inside queries is something that our community also has been interested in already for quite some time. I mean, for example, there is this workshop called Data Management for End-to-End Machine Learning. They have their 10th anniversary at this very conference. Yeah. And so what these systems allow you definitely to do is to call the models inside the database. Sometimes they even compile model inference to SQL. Sometimes they use tensor computations, computation graphs from tensor engines to execute this SQL, etc. So this is also quite a lot of work that is happening there. Now, I'm talking here about compiling models, model inferencing to SQL. What is commonly done most of the time is that you have a specific model and you're going to compile it to a specific SQL expression that will do inferencing for that model. But actually, there is an alternative approach, which is what I would call a uniform approach, where you can express inference actually uniformly in SQL. What do I mean by that? I want to go a little bit into detail because this is connected to something I want to explain later in more detail. So if you have a model, let's say here a very simple neural network with one hidden layer, but so basically what you can do, what people do is store the weights in a table. Yeah? You can store the weights and the network topology, you can store it in a table with all the weights. And then basically your model is just in the database together with other data. And then what you can easily do, and this is very easily expressible in this is very easily expressible in SQL actually, and it works. This works out of the box. You can store a bunch of models in your database. You can store a bunch of inputs in your database. You have many of these tables. Some tables contain the model, some tables contain the data. And then doing inference is simply just an SQL query, and not even such a complicated one. If you know the number of layers, or you could use recursive SQL like I show here, if you don't know the number of layers. And we noticed, and there are other papers too, by various researchers, where we noticed that this actually works quite well. Yeah. There was even at last year's SIGMOD conference in Berlin, there was a very interesting system proposed called Alsacian, which really introduces optimization methods and execution implementation strategies where you really have this task, where you have a massive execution of many, many models stored in the database on many, many data stored in the database. So there is already activity there, and this is backed by improvements, extensions of query processing. So also here, I think we can say that also here we are doing our job as a database community. So in the first two levels of my taxonomy, administrative and applicative, I think this is well understood, and there are lots of systems efforts going on. So let us now move to the third level of the taxonomy. And this is what I call behavioral querying. Okay, behavioral querying. This is, there we are looking at, let's say, more higher order queries, if you want. We don't want just to call a model on data, which is called inferencing, but we want to really inspect the semantics of this model. I mean, a machine learning model represents a function. In the end, at the end of the day, a machine learning model represents a function that was learned from data. Yeah? And here, let's say it is just a numerical function that goes from vectors to vectors, D vectors to P vectors, where D is the input dimension and P is the output dimension. And for example, one question you could ask about that function, so it is a query, but it's a question about the function. You can ask, for example, a property that is known as robustness. Suppose I have a certain input, and I would like to know if my function on all the inputs close to that input have a similar output. Yeah? So if x is close to a, then f of x should be close to f of a. Yeah? That's a property that may or may not be true of my model. Yeah? So it's a query. It's, in this case, even just a yes-no query on a model. Yeah? Now, this robustness, many of you will know that, but still I will say, this robustness actually came about around, let's say, 15 years ago in a paper where people mentioned and noticed that like the early image recognition models were not at all robust. For example, if you just took an input of an image very close to the image of a school bus, then suddenly that other close image would be categorized as an ostrich. Yeah? and so that's definitely not robust. That's the counterexample of robustness. And so when these kind of properties, they were called by the original authors, were called intriguing properties. Yeah? When these properties of neural networks came about, people started to think of other properties that you may want to ask and to check about models. Yeah? Whether your models actually have the properties that you expect as for your application that are important for your application. Yeah? And there are many of them. Yeah? So I talked about robustness. Another very popular property that is very popular in what is called explainable AI, yeah, is called counterfactual explanations. So you have an input A, it has a certain output, f of A, yeah, and you would like to know, are there any x's close to A, as close as possible, not too distant from A, that have a different output. Yeah? So now we are flipping the inequality. Yeah? That is supposed to give some kind of explanation why A had the output it has. Yeah? Because not too distant x has a different output, and so then you could compare this x with this A and maybe get an understanding what your model is doing. Yeah? Other properties, for example, suppose you have a certain safety threshold on your model. You don't want your model to go beyond some kind of safety threshold, and you want to say, yeah, f of x always has to be less than 120. Yeah, we just take some random example here. Yeah. That's also a property that you want to know whether it's true or not about your model. That's a query. Monotonicity, for example. You have a function. Let's say a very simple function, in this case a one-dimensional function, and you want to check whether this function that is represented in the model that was learned from data is actually monotone or not. Something you may want to know. Or you want to know, for example, sorry, I go one too fast. Sorry. Last one, for example, is suppose you want to check whether your function is sensitive or insensitive to a certain input. This is a very simple example here that I have of a function with just two inputs. And if that property is true, actually the second argument doesn't matter at all to the function. As long as the first argument is the same, fxy and fxz will be close. Yeah? That's also something that you could check to check. Now, so this is just a list of properties. The list of properties that you can think of is endless. Yeah? And people have been working on that, but not in databases. Yeah? People have been working on that in the field of neural network verification. And so there is an active community there that is mostly, I would say, focused on robustness, but is also considering other properties, and there is an active community there that is trying to solve these problems. But our motto today is models are data too. See? So my point is that when the models are data, live in the data system, they should not be left just to some completely disjoint verification thing. These are simply becoming analytical queries, like we are used to having analytical decision support queries, complex queries about complex data, And these are just like that. They're not that much different, I would say, from analytical queries on ordinary data. Now, even if you don't buy my proposal of managing models in the data system, and models are data too, even if you don't buy that, you should still be interested in querying the behavior of a model. Because basically, let's take a simple example. I mean, assume you just have a classifier model that is trained on data. It classifies, for example, shall this profile of a user, shall this profile of a client get a loan or not? I mean, that's a classical example of classical machine learning. So we train this classifier on training data, and then we will actually apply it to other inputs. And every input that you give it is either true or false. So this is basically just an infinite table. It is a table of all the input vectors that are classified true. It's an infinite table. It's just a relation. Yeah? It's a relation with D columns. For example, I mean, take another example. Take social network link prediction. Yeah? Suppose, just for the sake of the simplicity here, suppose that every node in a network is represented by a vector in just with 4 dimensions. Yeah? Then the classifier who will do the link prediction will take 2 nodes, so it will take an 8-dimensional vector and produce 1 or 0. Yeah? There should be a link or there should not be a link. Yeah? So that's then the case in that example, D would be 8. Yeah? And that's an infinite table. Eh? Why not query it like it was a finite table? Yeah? For example, we may want to check, given 2 nodes, A and B, are A and B connected via one hop, one intermediate hop? Yeah? That's a classical, are A and B connected via a common friend? It's just a self-join on that infinite table. Does there exist an X so that you can go from A to X and from X to B? Yeah? And this is a very simple conjunctive query that you want to ask about this table. Yeah? So I think querying the behavior of models comes very naturally once you think of it from a database point of view, database perspective. Okay. So that is behavioral querying. I hope I kind of made it clear what I mean by that. There is one more category in my taxonomy. Now, by the way, these categories are not strictly increasing. I mean, in general, you can think of queries that combine all the 4 categories. But the last one is where you are also actually want to look inside the models. So far, I mean, the properties that I presented before now about behavioral querying are all what is known in machine learning as a model agnostic. I mean, they just view a model as a representation of a function, and we're just asking questions about that function. Yeah? But sometimes you really want to look inside the representation, look inside the model. For example, people do neural network pruning. Yeah? You want to know whether there are any useless connections or any useless layers or useless neurons in a model. And in a sense, that's also a complex database query, right? Once the model is data, it's just another query. Yeah? Give me the neurons that are useless for this training data or maybe in general. Yeah? Also, like, I mean, basic operations on matrices, on weight matrices in machine learning, like the backpropagation operation, yeah, that you do, that is basically also a query. Yeah? And people do that. I mean, there have been work in our community on doing backpropagation inside a database system. Yeah? I was mentioning this model atlas before, where you have this huge graph where every point is a model. So, for example, looking inside the models and determining whether there should be an edge between 2 nodes, 2 points or not, for example, based on distances between the weights. Yeah? That is also, you are going to have to look inside the models to do that. Yeah? And so I was mentioning that in machine learning there is interest in data mining kind of queries on this model zoo, on this model graph. Yeah? And so, yes, these are also typically things where you have to look inside the models, for example, inside the weights to determine what structure is present there. So that is my last category, and like I said again, typically these categories will flow into each other. I mean, queries will have aspects of all 4 of them, possibly even. Yeah. So that kind of concludes my taxonomy, and the message so far, I think, at least my view on this, is that for the first 2 categories, there is lots of work from the database perspective, but in the last 2 categories, there is much less. There's much less, from our perspective, work on this. Yeah? And I think there's a lot of potential there. Yeah? I put a small asterisk there, because there are really very few, at least that I am aware of, papers, work, research on behavioral and looking inside querying of models. One of the few examples one of the few counterexamples is work done by Arenas et al., where they look at Boolean models. Yeah? And this is worth much more than a footnote, but it's just a footnote here. But actually, their work is worth a keynote in themselves. And actually, the keynote already happened. I mean, like 2 years ago, the PODS keynote was given by Marcelo Arenas on that work, so I will refer to that, and I'm not going to talk about it. But let's say this is one of the few papers for the moment in the PODS community, but I think Sigmund and PODS here should do that together, yeah? Where you're going to try to do support behavioral and inside querying of models as data. So after this taxonomy, I would also like to take a little bit of time to present some of our own work in that area. And so I summarize this as saying that SQL can verify neural networks. Yeah? This is a result that we obtained last year, and I want to present this to you on a very high level here too. So, first of all, I want to introduce a benchmark logic, I call it. This is a query language for expressing properties about functions. Yeah? And this logic is called first order logic over the reals with linear arithmetic and a function symbol. Yeah? That's a mouthful, but it's really very simple. Yeah? Basically, this is a logic that is built from linear real arithmetic constraints, which are very popular in SMT solving, for example, in SAT solving. Then I have my function symbol. Yeah? That's the function symbol I want to talk about. Yeah? And then I just have logic. I have and or not, and I have quantifiers, but be warned, the quantifiers range over numeric inputs. You want to be able to talk about arbitrary numerical inputs. So these are quantifiers that range over, let's say, the whole set of real numbers, or if you want, the whole set of rational numbers. Now, this logic, I should give some examples of formulas in this logic, but I already did that. I mean, all the examples I gave of properties of behavioral querying, these are all examples written in that benchmark logic. Yeah? Okay. And you see what I have here. I have logical connectives, I have linear arithmetic, and I have my function symbol, of course, that I'm talking about, and I have my quantifiers. Okay? So this is a nice logic because we don't then have to focus on 4 or 5 or 6 properties that we want to verify. No, we now have a general logic that we can talk about that can express many, many desirable properties that we may want to check. Now, I call that black box logic. Yeah, you see that here. Why? Because you just have a function symbol f. It's a black box, but you can query it as much as you want because you can quantify over all possible inputs and express lots of properties. That's why I call it a black box logic. So that is benchmark logic. It's not really meant, I don't want to propose this logic in the first place as an actual query language, although it would be nice. It would be nice, but there are some caveats. Let me explain a little bit just what is possible and what is not possible. In principle, this black box logic is effective. I mean, you could in principle use it to query functions. I mean, assuming, of course, that the function itself is definable using linear real arithmetic, and if you have now a black box query, then you can actually effectively compute the answer. You can reduce this to linear real arithmetic constraint solving, which is something that is in principle possible and is even implemented in so-called SMT solvers like the very popular Z3 constraint solver. So in principle it's possible. Yeah? And for example, if you're interested in neural networks with ReLU activations, yeah, feed-forward neural networks with ReLU activations, well, the functions that such networks represent are definable in linear real arithmetic. So that's applicable to that context. So in principle, black box querying is computable, but there are caveats. I mean, first of all, complexity. Yeah? By using these ReLU activations, I assume most of you know what the ReLU activation does. It basically tests whether something is positive or not and does two different things. And so if you want to express that in the black box logic, you get basically two cases. And so your formula will blow up. If you have nested ReLUs, the formula will blow up and you will get very large formulas. Now, people are aware of that, and this linear real arithmetic solving community, they have algorithms. The algorithms are basically very related to linear programming feasibility. This kind of algorithms, it's almost the same problem actually. And people, for example, Guy Katz, who is very famous in this field, has developed adaptations of the simplex algorithm to deal with this ReLU problem called, he called it ReLUplex. It's a very famous system that is implemented, for example, in this Z3 solver, SMT solver. But still, I mean, that's maybe just for existential quantifiers. Yeah, I mean, there are some improvements, but even without ReLU, I mean, in general, solving this black box logic with arbitrary alternations of existential and universal quantifiers, I mean, this is still an inherently exponential problem. So, in general, that's a huge caveat. Now, however, we were not really deterred by these caveats, and we still wanted to understand, in principle, what is possible, right, with this black box logic. And so, like I said, we are going to store models in the database. So we're going to store them in tables. We're just going to store the weights in tables, yeah? After all, let's say a feed-forward neural network is just a finite sequence of matrices. Yeah? We can easily store matrices in a database. Many people do that. You can just store it in a relation, row, column, weight. Yeah? You store the matrix in a table. And so that then allows you to use SQL. Yeah? So the model is just a table. The model is just a table. We want to query it, so we can use SQL. So our question was, how does this black box logic relate to SQL, which is, you could call a white box logic, because the model is there in your face. It is completely, all the weights, all the connections are there, stored in the table. So this is not a black box logic at all, it is a white box logic. And we know SQL very well. So how do the two logics relate? And our main result presented last year at the International Conference on Database Theory is actually that every black box logic query over these kind of feed-forward ReLU networks can be expressed in SQL. So SQL can verify neural networks. Yeah? There is a warning here. We assume fixed depth neural networks, so the number of layers, the depth of the network is assumed to be known, but not at all the layer size. So you can have as many hidden units you want in every layer. Yeah? And by SQL, what do I really mean by SQL? Because of course SQL is a big language. I really basically mean just the relational algebra with aggregates and arithmetic and elementary arithmetic. Yeah? That's all I need. Yeah? Okay. So I think this is a nice result that shows that at least in principle we should be able to support complex property and verification of neural networks, because in principle SQL can do it. Yeah? That's the message. I don't know how much time I still have, Floris. I think still have 15 minutes, but there should also be questions, a little bit time for questions, right? 15 still? Yeah? Okay. Including questions, eh? Yeah. Okay. Yeah. Yeah. Okay. So, but I'm almost at the end. But so, I want to say just two more things. So, first of all, if you're wondering about what happens when the fixed depth assumption is lifted, what can we do? What can we not do? Actually, we have a paper also this afternoon on that. Yeah. So, if you're interested in lifting this fixed depth assumption and actually learning about all the problems that occur, then you should come to our afternoon session. But I also wanted to give a really quick idea of how do we actually prove this, because this is actually, I think, very interesting, and it also relates to my younger self. I mean, where I played around with encoding relational algebra expressions in relations and seeing what you can do in the reflective relational algebra. And something very similar happens here too. We're going to use relations to encode formulas, linear real arithmetic constraints. We're going to encode them in relations, yeah? And then play with SQL to manipulate this. That's basically the idea. Yeah? Just very quickly, suppose you have a relation. I'm going to give the three main steps of the proof, but it is a very high level, don't worry. Suppose I have a relation that contains my network. Typically it will be several relations, but let's just call it one relation M. Yeah? So first thing we have to know, to understand, is that oh no, actually no, I'm going to skip this, because I want to say, well, okay, I will go very quickly. Every unit in this neural network represents a piecewise linear function. Yeah? What is a piecewise linear function? It is basically a function definable in this linear real arithmetic. Yeah? And we can actually, from the model that we don't know, it is in the database, we can actually encode the formula that defines this function. We can encode it as a relation and define this as a view in SQL. So we can retrieve basically the constraint that defines this piecewise linear function, yeah? In relation, encoded in relation. Then a second thing we have to do is we have our black box query, right? We want to somehow compile it into SQL. That black box query contains lots of calls, if you want, but these are calls on variables. These are not actual calls, these are calls on variables. They contain atoms with variables v and u. And so what I have to do now is to go inside this encoding and replace basically those atoms by the actual representation of the linear real arithmetic constraint. So replace these atoms by the result of my SQL view. Yeah? And finally, then what I have basically is a representation of a quantified linear real arithmetic formula. And a very famous algorithm to solve these kind of quantified constraint is the Ferrante-Rakov algorithm. It's a classical algorithm. It exists already a long time. And actually, we checked that you can actually completely simulate this algorithm in SQL. Yeah? And so that's basically the proof. Yeah? Now, there are some comments here. A small comment is that we encode models and formulas in relational structures, right? And so I think that is very interesting. In a sense, we have adapted technique from mathematical logic that is called interpreting one structure in another, and we have basically adapted that to SQL. Yeah? Now, that is a technique in mathematical logic that belongs to the field of mathematical logic called model theory. So basically, this is model theory squared, right? It's model theory about models. Yeah? So that's a pun I couldn't resist. Now, does this work in practice? Of course, you will all ask. The answer is no. I mean, because there's basically not any work being done there, systems work being done on that field. This is just a principled question. But I will give you just a glimpse of what may be possible, right? There are lots of opportunities here for clever systems work and better algorithms. The theoretical construction, of course, produces monstrous SQL expressions, yeah? But I think there is a lot of opportunity here. And one opportunity I want to explain to you briefly is the idea of not using, I mean, nobody forces you to store a model as just the weight matrix in a table. You can use much more clever representations of the model in the data system. This piecewise linear view, for example, you could materialize it in convenient formats. After all, a piecewise linear function is basically a simple arithmetic function on polytopes. I mean, space is divided in polytopes, and on every of these polytopes, it is an extremely simple linear function. So we can take advantage of that, then maybe use algorithms from computational geometry and integrate them into a query processor. I think this is really something that is feasible, that is possible. Yeah? It should be investigated. I can illustrate that in the 1D case, because that is so simple. There it just works out of the box. There it just works out of the box because it is extremely simple, of course. I mean, if you have a 1D function, just a function from R to R, one input, one output, yeah, it's very simple. Then the piecewise linear function just looks like this, right? It just looks like a function that is piecewise linear. And you can very easily retrieve all the breakpoints and the slopes of these pieces by a very simple SQL query, just from the weight matrix. This is very simple, and it works out of the box, and it works efficient in that case because it's so simple networks. Yeah, and then you can do various verifications. Yeah? For example, you want to check if the function is monotone. Just very simple query on these breakpoints and slopes view. Trivial SQL query. Yeah. Another one, the boundedness property. So is within certain bounds, is my function safe? Is it within thresholds? Yeah, not too complex decision support query, right? Of course, like I say, this is a very simple case, but it shows that there is potential. Yeah. Good. I'm almost done. I'm at my conclusions. Yeah. So I presented to you a new class of complex analytical queries. There are many challenges, many open problems. Yeah? So we have to design good algorithms. We have to design query languages, but most of all, we have to think about systems work. I mean, good implementation strategies. Of course, the obvious thing is to also look at other model classes. Yeah? Transformer architecture is, of course, an obvious one. Yeah? We can think about expressive power. So what kind of queries can you actually express and which one can you not express? This is typically something we do at PODS. We want to understand our languages, the power of them. And this actually ties back to something that was very active around the last turn of the century in database theory. That was a field called constrained query languages, which was also about querying these kind of infinite tables. And you see now that this comes back. Yeah? This comes back now in this machine learning context. So it is worthwhile to revisit those techniques because that kind of work was somehow suddenly stopped for no good reason. I mean, we know that, right? I mean, research is trendy. Suddenly, after 5 years, we suddenly all start doing something else. And that doesn't mean that everything was solved. Not at all. Eh? And so it is certainly worthwhile to revisit that in this context. Query processing optimization, obviously. Eh? And I want to end with a small note going back to how I started. This vision, maybe we can also try to revive this dream of Jim Gray, querying code and managing code in databases. I still think this is a very natural idea. Yeah? And for example, in the software engineering community, people are interested in that. People are really interested in querying code, and they have their own approaches. But they really can use our help, I mean, because they don't really know how to design a query system, and we know perfectly how to do that. So with that, I conclude, and thank you for your attention.
Thank you, Jan, for the nice keynotes. If you have any questions, please use the microphones in the corridors, so just start queuing. Thank you.
Hi, thank you for the nice talk. was just wondering, there is a lot of work and competition on inference for large language models and other foundation model. Do you think we can build a database management system that can replace those execution engines and be more efficient, cheaper, and faster?
So you're talking about large language models, or yeah?
Mostly large language model. This is the trend, right?
Well, yes. I mean, if you're just talking about inferencing, yeah, within a data system, like I said, I mean, that belongs to the category of applicative model querying.
Right.
I think there is already quite a lot of activity, and many people here in the room that know much more about that than me. There is a lot of activity on that front already. Yeah.
I mean, do you think that there can be the choice, I mean, the first choice when someone wants to do inference on those models?
Yeah, I'm not in a position to predict how systems will actually be in a few years and whether they will be able to meet that challenge, but definitely people are hoping for that and are working on that. Yes. For example, just yesterday, I mean, this is slightly different, but also very related. Yanis Papakonstantinou also argued actually for that kind of work. So yes, people are very interested in that. But I'm more a theoretician, so I'm not really in a position to say, yeah, in 5 years systems will solve this or not. No, I don't know.
Thanks.
But people are very interested in that.
Right. Thank you.
Hi. So my question is twofold. Can you hear me?
Yeah.
So basically, whenever we say models in machine learning, they are usually saved as tensors, and most of the operations that we do during inference or training are much easier and faster to do there. So if we store data in like relational databases or as tabular data form, so it will like the first problem would be those operations would not be that faster to do now. So that's the first problem. And the second problem will be that it will include additional information that we have to save rather than saving in a tensor. So we'll have to save information about rows and columns, like which layer it is part of, this weight. So wouldn't that be a problem in scalability? And if, how do we like combat that?
Yeah. So if I understand correctly, your question you say, how do you somehow bridge the architecture of a SQL system with the architecture of computation graphs, which is used in TensorFlow and Onyx and all these systems, right? And people are very actively working on that to make that bridge. And indeed, the similarities are are clear, right? I mean, both use query plans, basically, both use optimization. And I think these two can and will be married and are already being married in actual systems now.
Thanks for the presentation. I think storing weights and biases in a database, to me, it makes sense, and it's also interesting for the database community. You have new things to do. My question is, what is the next step to have an impact outside of the database community? Just querying it will make us happy, but did you try? Now you have a query language, suppose it works, and I think it will work if you try hard enough. What can we do for making machine learning models better? So in the end, you want to classify something, and you want to see, can I query something, which weights don't work so well, which weights work, where is dropout better? With your query language, can we then make inferencing better? Can we make the models more compact, storing it smaller, then we have smaller models, then we get the big models on our machines? Did you think about this one? So not the impact on the database community, which we all understand, but the impact on the machine learning community, what our query language would give them, and how it would make machine learning models better, more efficient, more robust, better insight.
Yes, I think that is the vision. It is not just for ourselves. It is to make machine learning models verifiable and then improvable. And if we notice that, so our tools could be used to verify the models that are trained, and undoubtedly, sometimes they will not satisfy the constraints we want, and so it will be a feedback, right?
Do you have some examples already where you show that it works? Or
No.
That's the beginning at the moment?
No, this is very early. No.
Okay, so this is the historic moment.
Yeah,
okay.
I'm just honest. Yeah.
Very good, thank you.
Hello, thank you for the fascinating perspective. So I have an additional meaning for the word model. So many statistical models, right, they will encode as well assumptions about causality. So I was wondering what would be your take on that?
Yes, so you're talking about causal models. Yes. Yeah, that is indeed one I forgot on my list. Yes. I think for what I've been talking about, I think causal models are not so related. Yeah? But for example, Angela Bonifati, I mean, one of the esteemed members of our community, she's actually developing a whole research program on actually querying causal models. Yeah? So that is, in a sense, fits in the same broad program of querying models, basically. But these are still quite another animal. I mean, these causal models, not really comparable to machine learning models, although there are certainly possible links. I mean, everything is linked in the end. But thanks for your suggestion. Yeah.
Thank you.
Hi, Jan. Thanks for the talk. I was wondering, I know you really like in the end that you can do it fully in normal SQL, but I'm wondering if in the way you encode the model, if there's any ideas that you have for how to extend SQL by sort of new operators, new things to make this smoother and maybe more amenable to optimization.
Yes. So that is probably going to be part of making this practical. Eh? So because in principle it is doable in raw relational algebra with aggregates, but I mean typically what you want to do is detect certain patterns in your query expressions and then optimize them, and then it would be, of course, much easier if you added specific syntax for that. But I don't have, off the top of my head, no concrete suggestions for this, that kind of syntax yet. Okay. But it's definitely something that should be done.
Okay.
That microphone. Just be waiting for a while. I didn't know there was a microphone there as well, so I'm sorry.
Good morning, sir. Absolutely loved the talk. So I have a question regarding representing the model lakes as a huge graph where each data point is a model. So, and ages are being decided according to the relations between the models like weights. So my question is, because models are evolving very fast, all the models are evolving very fast. So is there will be situation where ages are being removed and added continuously, and also all new models have been will be added. And if a new data point like a model is added, so we have to decide what are the ages. Then what is the scalability? How the scalability is going to be affected?
Yeah, that's an interesting question, actually. So I've been, it was a bit of a side note, actually, this model zoo thing, this model atlas. But indeed, I mean, there can be lots of more interaction between the database community and the machine learning community. And what you are basically asking, I think, is incremental maintenance of such model atlases. Yeah? And certainly, I mean, we can help with that. And I think, yes, it is a very good point that this has to be done. And this is a real problem. So yeah, it's a good topic to work on, I would say.
Thank you, sir.
Maybe just two very, very small questions.
Okay, I will try to keep it as short as I can. I was actually also going to ask about the word model, because this is one of the most interesting things I think about this presentation. On the one hand, you were saying that it's one of your big pet peeves that this model word is so overloaded and can refer to 10 different things. On the other hand, I think this presentation would not be possible without it. You could not be talking about models for querying models, for example, and refer to so many things. So do you think it's maybe a good thing that we have such a plural concept and can, you know, investigate in this way, or is it maybe better for the community to specialize our terminology of model going forward?
I guess we can live with all these different definitions. We're smart enough to keep 5 meanings in our head. It's just the way it is. And yeah, I didn't propose a new vocabulary. So yeah, it's an interesting thought, but yeah. Thank you. Thanks.
I want to ask about the model zoo. It's a really interesting concept. So I want to ask, like, for example, a model zoo is a repository of pre-trained models. So in the model lake, you have a lot of data sets, you have the pre-trained models. But many times, the reason we have a model zoo is because we want to transfer learning. For example, when you have a new data set, you want to know which pre-trained models I should do fine-tuning. So now my question is, have you ever thought about, like, I develop a new language, like I express different models with this language, and such that you can tell which two models are more similar for transfer learning? Because in machine learning, they just compute transfer score.
Yeah, okay. Yeah, that's an interesting suggestion. So if I can rephrase your question, so you suggest declarative languages to guide transfer learning, giving a property that you want that is maybe not there yet, so that the model can be transformed in some way. Yeah.
Yes.
Yeah, it's a very interesting suggestion. Yeah, thank you.
Okay, thank you.
Okay, thank you for the questions. Also, thanks, Jan again for the talk. Wait. One moment before we go, I have like a very short announcement. Like PODS, the PODS sessions after this one will move to the next room. That's one important thing. And the second thing, I've been asked to do some local tradition celebration of the keynote speakers. So I will try to do my best to honor the tradition. Oh, wow. This was in France. So actually, I think that's what I was afraid of. Wait, one more. This is for eternity. Let's thank Jan again. So thank you, Jan. Okay, that's it. Thank you very much for attending the session, and see you around. Thank you.